ever wonder why rework can seem so difficult and frustrating and tedious? Do you ever think there must be a better way? Well, our good friend Ray has some interesting secrets to pass on that will make reworking through-hole and surface mount solder joints a whole lot easier. Probably the most important secret for solder rework technicians is to avoid reworking solder joints unless it is absolutely necessary. That's because there can be potential damage to the component, the circuit board, and any adjacent solder joints. Every time the assembly is subjected to heat, its physical properties can be degraded. The adhesion between the resin and the laminate and the copper lands on the surface of the board can be weakened by heat. Excessive heat and unnecessary force, caused by pushing with a soldering iron or by attempting to remove a component before the solder is completely melted, can cause the land to separate and lift off from the board. A lifted land can be very difficult to fix. Your customers may not even accept this type of rework, which means the entire assembly may be scrapped. Of course, we will need to fix the obvious problems that keep the product from functioning, but we definitely want to avoid any cosmetic or unnecessary touch-up operations that can create more serious problems than they cover up. At this point, let's review the typical tools and materials used during rework. We'll begin with the hand soldering iron. There are a variety of temperature-controlled soldering irons, maybe even within your own company. Perhaps the most important thing to remember is to always keep the temperature at a safe, controllable level during any type of rework operation. 315 degrees C is a reasonable starting temperature for most hand soldering operations. Cleaning and tinning the tip of your soldering iron is equally important for proper heat transfer and tip life. Always remember to wipe the tip on a clean, damp sponge or brass sponge and then apply a light coating of solder before you begin any rework operations. Now let's talk about soldering flux. Flux is an essential ingredient in the soldering process. Its purpose is to remove oxidation, which can prevent proper wetting or bonding of the solder. It can also be helpful in transferring heat between the tip of the iron and the component lead and land. The next rework material is solder braid. Solder braid comes in different sizes or widths for various solder removal operations. The braid is made up of copper strands, which can be unfluxed or with a powdered or dried flux inside. When the braid is heated by the soldering iron tip, the molten solder will be drawn up into these copper strands. Once again, your company will supply you with the solder braid that's compatible with your soldering and cleaning processes. Another tool that serves the same function is the vacuum extractor. This tool has a heated tip with a hollow orifice or hole in the center. Attached to the back of the tool is a flexible hose, which vacuums the liquid solder into the storage chamber inside the tool. For surface mount rework, the more sophisticated removal tools include thermal tweezers, hot air pencils, pulse heat tools, and complex rework stations. This video will examine some alternative methods that make through-hole and surface mount rework even safer and easier. Ray's secret topics include destructive removal of axial or radial components, removal of dip components with thermal tweezers, using a solder fountain to remove multi-pin connectors, using a low-technology rework station to safely remove surface mount components, and tips for reworking ultra-small surface mount components. During these topics, we'll show the correct way of performing the more difficult normal method of component removal. Then we'll explain all the bad things that can happen during the conventional process. Finally, we'll show how fast and simple Ray's technique is. The biggest risk when performing through-hole rework is damage to the barrel of the plated through-hole or damage to the laminate. The IPC 7711 Process Goals and Guidelines specifies that rework operations should be a non-destructive procedure, meaning that the component should not be damaged during the removal process. That's because there are many times when a replacement part is extremely expensive or can't be obtained. In these situations, the original part needs to be used again. However, when replacing something like an axial leaded through-hole resistor, there are usually new replacement parts readily available that virtually cost pennies. The replacement of these components does not justify the additional time and risk to the circuit board assembly that occurred when using the 7711 process. Ray's secret is that destructive removal is bad for the component being removed, but much safer for the circuit board assembly, and faster than non-destructive removal. Let's begin by examining the proper method of doing non-destructive removal of an axial component with fully clinched leads. There are several techniques for desoldering clinched leads. We'll need to bend the lead upright before we can desolder the entire joint properly. On fully clinched leads, you may have a problem getting the tip of the desoldering tool underneath or around the lead without damaging the land or the board. There are 3 alternate techniques for desoldering fully clinched leads. The first method uses a thermal parting tool with a flat end tip. The tip of the parting tool can be used to melt the solder and then bend the lead upwards. It's a good idea to unclinch the other lead at the same time, so you aren't constantly shifting tools back and forth. Now we're ready to use the vacuum extractor to desolder the component. When you apply heat under the first connection, the solder should melt rather quickly. At that point, you'll feel the tip drop down onto the land. Now move the lead around in a circle without applying pressure onto the land. As the solder melts, the lead will move more freely. Upon complete solder melt, press the vacuum switch to draw the molten solder up into the handpiece. After the solder is removed, continue to move the lead around in a circle with the vacuum still on. The fast-moving air will now cool the metals inside the hole. This will also make sure that the liquid solder is drawn all the way into the vacuum chamber rather than stopping inside the tip. After 1 or 2 seconds, you can remove the tip, then stop the vacuum. You can also use a chisel tip on a hand soldering iron to perform the unclinching process. We begin by selecting a small double-sided chisel tip. Then we position the tip at the end of the lead. Once the solder melts, push the lead straight up. The third technique uses the vacuum extractor and a pliers to straighten a fully clenched lead. We begin this process by placing the tip of the vacuum desoldering tool against the junction of the lead and the land. When the solder melts, activate the vacuum. At the moment, we're only trying to remove the solder that connects the clinched lead to the land. There may be a slight solder bridge remaining between the land and the lead after this desoldering process. If this bridge is relatively small, we'll take a flat nose pliers and gently twist the lead to one side. You should be able to feel when the lead is completely free from the land. Then, bend the lead upright in preparation for the vacuum desoldering operation. Now we're ready to desolder the remaining lead. Let's do it in real time to demonstrate the proper sequence and timing of the operation. First, we apply heat. Feel the tip drop down, move the lead around, activate the vacuum, remove the tip, and stop the vacuum. The component should now be ready to remove. It should offer no resistance at all. As you can see, non-destructive axial component removal is a fairly complex process, even when everything works perfectly. Now let's look at some of the problems that can happen during this process. Regardless of the technique you use to unclinch the lead, you can easily tear the land away from the board. This is not a desired result. Improper use of the vacuum extractor to desolder the lead can also cause problems. For example, staying on the connection too long to remove the solder can create measles, burns, and delamination. In addition, during the solder removal process, some residual solder may remain in the barrel and the lead can reattach to the side of the hole. This is called a sweat joint. If you try to pull the sweated lead out of the hole, some of the metal can be ripped right off the barrel wall. A damaged barrel can be difficult to repair and the entire assembly may need to be scrapped. As you can see, it takes a highly skilled solder technician to remove an axial component using these non-destructive methods. Now let's see why Ray's technique of destructive removal is safer and takes less time. The first thing we do is simply cut the leads of this axial resistor. Next, we turn the board to the solder side and use a soldering iron to heat the connection area. Then, we remove the remainder of the lead with tweezers. Let's watch that technique one more time on the second lead. The last step is to use a solder braid and a soldering iron to wick any remaining solder from the holes. And that's all there is to it. The resistor can now be replaced. The vacuum extractor can also be used to remove any remaining solder from the holes. As you can see, this secret deserves to be shared. Now let's check out the way Ray prefers to remove multi-lead devices, such as dual inline packages or dips. The secret is that there are other non-destructive removal methods that are much safer for the substrate and much faster than conventional non-destructive removal. We'll begin by reviewing the conventional dip removal technique using a vacuum extractor. Remember, dip components have 2 rows of flat leads. For flat leads, the vacuum tip needs to be sized so that the width of the component lead will fit inside the desoldering tip. The tip should not hang over the edge of the land whenever possible. We can perform an optional flux application onto the component leads on the solder side of the board. We're ready to start at one of the corners. You'll often find that 2 of the corner leads will be partially clinched to hold the dip in place prior to soldering. Typically, these partial clinches can be desoldered with the vacuum extractor. Starting on the clinched corner lead, we'll angle the vacuum tip parallel to the lead and then push the lead inside the tip as the solder melts. When the solder joint is molten, we can bend the lead upright and position the tip squarely onto the land. After the entire joint is melted, we'll move these leads back and forth, rather than around in a circle. Then, activate the vacuum and continue drawing air through the hole to cool any residual solder. After we remove the tip, continue the vacuum in order to draw the solder all the way into the storage chamber. In order to avoid potential heat damage to the board, we'll need to skip around rather than desolder in a continuous line. Some people prefer to desolder the corners first. Then they proceed to alternate back and forth in this same pattern. Others simply skip every other joint and work their way around twice until the job is completed.